Okay, let's get started, please. So before we go on, I want to say a little bit about, so in case you haven't seen trigonometry in right triangles before, everybody close your eyes for a second. Who has seen trigonometry in right triangles before? Okay, put your hands down. Okay, thank you. Okay, so some people haven't, so that's okay. So I'm gonna backtrack a little bit to some material from 6.5 trigonometry with right triangles. Okay, and this is not gonna take long. Okay, so let's remember how we defined the cosine and the sine, right? We said we have an angle, theta, and then we define the cosine and the sine by taking the unit circle and then taking this point of intersection, and then the cosine was the x coordinate, right? And sine was the y coordinate, right? So whatever, right? This point has some coordinates, x and y, right? And those points lie on the unit circle, right? Because that's how we define them. And we let cosine of theta be x and sine of theta be y. Okay, so that's our traditional, or maybe non-traditional definition of the cosine and the sine. Okay. What's often done in high school is to introduce the trigonometric functions using triangles, using right triangles. So you do something like this. You say, okay, suppose I have a right triangle and I have an angle. Okay, then we call this side the opposite. We call this side the adjacent. Right, and we call this side the hypotenuse. Okay, and okay, and the way that sine and cosine are defined in this world are, you say, okay, the sine is going to be the opposite over the hypotenuse, the length of the opposite over the length of the hypotenuse. So you take this and you divide it by this, right? The cosine is going to be the adjacent over the hypotenuse, right? And the tangent is going to be the opposite of the adjacent, right? We know tangent is, of course, sine over cosine, right? So sine over cosine, which works out to, opposite over adjacent. So that makes sense. If you accept these two guys, then that third one makes sense. Okay. So for example, right, if I have a right triangle, a 5, 12, 13 right triangle, and I'm looking at this angle, well then, cosine of theta is going to be adjacent over hypotenuse, and sine of theta is going to be sine of theta is going to be opposite over hypotenuse, right? And if I looked at this angle here, let's call this angle alpha, say, cosine of alpha would be the opposite, the adjacent over the hypotenuse, right? And sine of alpha would be the opposite over the hypotenuse. Opposite over the hypotenuse. Right? So this should be a 13. Okay. Okay. So this is how one can calculate the cosine and the sine using right triangles. You notice here that this actually gives us one of our trigonometric identities. This alpha, just as a side comment, this alpha is pi over 2 minus theta, right? Because in the right triangle, right, these two things add up to pi over 2. right? These two guys add up to pi over 2, because this is pi over 2, right? Everything adds up to pi. This sum of the degrees adds up to pi, right? And so what we see is that cosine of pi over 2 minus theta is sine theta, right? Cosine of pi over 2 minus theta is sine theta, right? Sine of pi over 2 minus theta is cosine theta. This was one of our identities that we saw earlier, and it makes sense in the triangle world. It's kind of easy to see in the triangle world. Okay. So, right. Okay. Is that making sense? Is that making sense? Anybody have questions? Anybody have questions? So, right. So let me just say why that's the same thing. Why are those two ideas the same? Why are those two definitions the same? Actually, before I say that, let me say that, before I get into that, let me say that this only allows us to define the cosine for angles between 0 and 90, right? It doesn't make sense to talk about an angle bigger, a 90-degree angle in a right triangle, right? So, so that's one sort of huge problem with this definition. You have to start making special definitions of like what happens if you're in this what happens if you have an angle that's bigger than 90 or a negative angle or stuff like that that don't really make sense for right triangles. Okay, that's why the circular definition is really the right way to do it. Okay, but for acute angles, right? As long as our angle is between 0 and 90, then this makes sense and it will match up with the circular definition. So. Why are these two definitions the same? Well, let's think. Right. If we have a right triangle, if we have a right triangle like this, and this is our angle theta, and we draw on it a unit circle. Okay, we draw on it a unit circle. Then our old definition says that. So here's the unit circle. Our old definition says that this length here is the sine, right? This height here is the sine, and this thing here is the cosine, right? Okay. So we've got this other stuff, right? Opposite, adjacent, and hypotenuse, right? And if we look at the ratio, right? Sine of theta as opposite over hypotenuse, so opposite over hypotenuse, right? Well, these are similar triangles, right? This triangle here and this triangle here are similar triangles. So the ratio is going to be the same. Ratios are the same. Ratios of side lengths are the same. So the ratio of this to this is the same as the ratio of this to this, right? So this ratio, opposite to hypotenuse, is the same thing as sine of theta over 1, right? So that's why we get this, right? This ratio opposite to hypotenuse is the same thing as this ratio here, sine of theta to 1. Because with similar triangles, right, this is the point from geometry. Geometry tells you that similar triangles have identical ratios, have equal ratios of side lengths. Right? The ratio of this to this is the same as the ratio of this to this, right? The ratio of A to H, right? If I look at A over H, well, that's the same as cosine to 1, right? That'll be cosine to 1, right? And tangent, right? O over A is just going to be sine over cosine, right? Sine over cosine. So you see that this this way of defining the trigonometric functions matches up with our true definition here. So this sort of restricted definition that just for angles between 0 and 90, works out. It's the same thing. So that'll be useful in what we're talking about today. So yeah. So just remember that that you can get the signs off of right triangles by looking at these sorts of ratios. Sine is opposite over. So there's some mnemonic that people use, like SOHCAHTOA. Right. So people use that as a mnemonic. I don't know. Have you guys seen this? Yeah. Okay. Okay, so yeah. Okay, so let's, with that understanding, let's go on to the last bit of trigonometry that we're going to do, which is 9.2. I think that's the last. Yeah, this is the last. Today is the last. If we finish it, it'll be all of the trigonometry that we need. Okay. So 9.2, law of sines and law of cosines. So these are our two final bits of trigonometry, and they're pretty cool. So let's deal with the law of sines first. Okay. The law of sines says the following, that given any triangle, I'm just going to draw one here. So we've got this triangle, and let's call the angles capital A, B, and C. Okay, and then the opposing sides, the opposing side lengths, we're gonna call A, lowercase a, B, and C. Okay, that's pretty standard. Okay. So the law of sines that says that given any triangle with the angles and side lengths labeled like this, then if you look at the ratio of the sine of the angle to the length of the opposite side, then that's constant. So no matter what angle you choose, the ratio of the sine of the angle to the length of the opposite side is going to be the same. So the sine of the angle over the length of the opposite side equals the sine of the angle over the length of the opposite side. It's always the same thing. Okay, so that turns out to be a constant. Okay, in problem 47, problem 47 in your homework, you'll see that it turns out that 3 points determine a circle, and that ratio turns out to be the diameter of that circle. Okay, that number, whatever it is, let's call it little d, turns out to be the diameter of the circle that is given by these 3 points. Okay, so yeah. Okay, so okay, so let's do some applications first, just to see how we would use this. So the applications are not the most interesting applications. It's sort of just like you'll see. So you are given you're given a triangle with angles pi over 3, pi over 4, and some last angle 5 pi over 12. 5 pi over 12. Okay. And the question is, and you know that this length here is 12 centimeters. Okay. And they'd like you to figure out this length. Okay. So you're given the angles, right? I mean, we don't even need this one. Right, you're given these angles, and you're given this length, and you have to figure out this last length. Okay. So this is just you know 3 parts of something, and what is the 4th part, basically, right? So so you'd say, okay, I know that sine of pi over 3 over 12 equals sine of pi over 4 over question mark. Right? And then you would just solve for question mark. Right? Or maybe I should have written this upside down. Right? I should have written question mark over sine of pi over 4 equals 12 over sine of pi over 3. Right? You can of course turn these all upside down. Right? If these guys are equal, their reciprocals are also equal. Okay. So then you just have to multiply both sides by sine of pi over 4, and then right, so then question mark is going to be sine of pi over 4 times 12 over sine of pi over 3, whatever that is. Right? Sine of pi over 4 is root 2 over 2, and sine of pi over 3 is square root of 3 over 2. Okay. So we get 12 roots of 2 over the square root of 3. Okay, so there's really nothing to this kind of question, right? It's sort of like, it's just a substitution thing, right? Right? You're asked for this length, and you know that the ratio of this, the sine of this angle to this, is the ratio of the sine of this angle to this, right? And so you just set those things equal to each other and then solve for the unknown. So this is it's just, algebra. Okay, number 15. Number 15 from your book is just a slightly more complicated version of that. So they give the following. Make sure to get these angles right. So you've got 50-degree angle here, you've got a 110 angle degree here, you've got a 95 degree angle here, and you're given that this length is 2, and you want to figure out these lengths, A, B, C, and D. Okay. So D is this short length here. A, B, and C are the sort of obvious ones. Okay. So take a look at it. Try it for a minute and see, think about how you would apply the law of sines to this to get, like, where would you start, right? What are you going to go for first, I think is really the question. Right? Where should you start? That's really the first thing you want to think about. Okay, talk with somebody, please. Okay, so let me ask, where should we start? Where should we start? And why do you think that's where we should start? Aaron.
I started by finding the angle opposite of 2.
Okay.
Because then you have like a complete
Yeah.
ratio. So
Yeah, so basically, so if you think of, like, basically we've got more information over here, right? We've got more information on this side, and so let's work from the easy parts to the parts, and then spread, sort of bootstrap our way upwards to rightwards to this part over here. Yeah. So you say, okay, well look, I've got 2 of the angles here, so that gives me the third angle, right? That gives me the third angle. Okay, I have to add up to 180. So we've got 160 here, there's 20 left, right? And then,
and then I did 2 over sine of 20 equals a over sine of 110.
great, right? Say, okay, now I can use the sine, right? I've got this angle, I've got this length and I've got this angle, so that gives me the ratio, right? That gives me the fixed ratio, right? And so that tells me that, for example, a over sine 110 is that, and it tells me that b over sine 50 is that, right? So that gives me a and b, right? Okay. Yeah. So so we can figure out those lengths, right? A is going to be 2 sine 110, 2 sine 110 over sine 20. B is going to be 2 sine 50 over sine 20. Right? And then what do we need to do to get this part over here? Well, we have B, at this point we have B, and we have this angle. We have this angle, right? So that gives us the ratio again, right? That gives us the fixed ratio, which is going to be B, whatever that is. I'm just going to write it as B. B over sine 95 equals C over what? C over this angle, sine of this angle. Well, what's the sine of this angle? I'm saying, what's the angle here? 70, right? Because this adds up to 180, right? So we got this over sine 70, right? And this is 165, so that gives us that this last angle is 15, and so we know that this is equal to d over sine 15, right? And then you can figure things out. Let me, okay, so you see that, the game is this is just, it's just a game, right? It's just a game where they give you, basically they're going to give you like, they'll give you basically 3 parts and ask you to figure out the 4th part. And you figure out the 4th part just by algebra, So that's all that's going on here. Let me put up one cautionary example. So I wrote these notes when my eyes were much better. Okay, so you've got a 45-degree angle here, and you've got this angle A here, and you've got 8 and 4 roots of 2 like this. Okay, and you've got this angle B. Okay, so the caution, so right, and so the question is to figure out what B is, say. Okay. And so what happens is you say, okay, well I've got a side length and the angle on the other side, right? So I know that sine of 45 over 8 is the same as the sine of B over 4 roots of 2. Right? Right? This is again one of those things. They give you 3 parts and you need to figure out the 4th part. So nothing spectacular. Okay, so now sine of 45 is root 2 over 2, right? And so we get sine of B, we get 4 roots of 2, and then everything divided by 8. Right? So we get 4 times root 2 times root 2, that gives me 4 times 2, which is 8. Right? 8 divided by 2 is 4, so we get 4 over 8, in other words, a half. Okay. So, so then, what's B? What's B? Well, B is the an angle whose sine is a half, right? An angle whose sine is a half. Do you know any angles whose sine is a half? $30, yeah, so 5 or 6 has a sine of a half, but so does 5 pi over 6, right? So 30 degrees, but also 150 degrees. So 30 degrees, but also 150 degrees. Okay, so the trouble, so sometimes it'll happen that there's more possibilities. So the thing is that B could be either one of these, right? B could be 30 or it could be 150 degrees. But looking at your situation, it can't be 150 degrees, right? Because you've got 45 degrees here, right? So sometimes there will be you'll get an ambiguous answer, and you need to figure out which one it is. So that's caution. Okay, so okay, so those are all the examples I wanted to give. Let's think about why this is true. Okay, so let's come back over here and think, why is this ratio constant? So why do we believe this? Why do we believe this? And this is always the question. Why do we believe this? Okay. So here's one way of thinking about it. Drop an angle. I'm sorry. Drop a perpendicular from B down to here. Okay, and let's call this length x. Okay. Well then, if we're using our triangle triangle definition of the sine, sine of A is going to be what? If we're using the triangles. Take 10 seconds and write down something. Just to reinforce the triangle definition. Okay, turn to a partner and say sine of A using the right triangle definition is going to be blah 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 over blah. Okay, what is it? Would somebody like to say? Or should I roll? I'm going to roll. Just to keep it there. Let's see. 6, 7, 8, 9. Melanie, it's you. Do you want? Do you know?
Would it be X?
X. So remember the SOHCAHTOA. It'll be X. So sine is going to be opposite over hypotenuse. So it's going to be X. X is opposite, and then you need to divide by hypotenuse. So X over C. X over C. Right. Okay. And then let's look at let's say sine of C. Sine of capital C, the angle over here. What's that going to be? Melanie, I'm going to make you do it. The sine of this is going to be
X over E.
X. This
X
is
over E.
this is an A. Yeah, X over A. So X over A, right? Okay. Now that tells me that I'm just going to multiply through here. C sine A is X. A sine C is X. Right? So those things are equal to each other. So C sine A equals A sine C. Right? This tells me that C sine A equals A sine C. Right? But then we divide both sides by C, and we divide both sides by A. Right? And we get sine A over A equals sine C over C. Right? We multiply both sides by we divide both sides by A times C. Right? The equality still holds because we did the same thing to both sides, and we get this. Right? And so that shows us that those two, this first one and the third one, are equal to each other. If we want to get the other guy, we have to drop an angle. We have to drop a perpendicular in this way, and then that'll show us that that maybe B and A are the same. That these two are the same, and so they're all the same. So we just do the same. Okay, so this is the law of sines. It's kind of cool. Is it okay if I erase this? Anybody still copying? No. Okay, I'll go here. That's fine. Okay, so the other thing we're going to talk about is the law of cosines. And this is actually much cooler, in my opinion, much cooler than the law of sines. In fact, I kind of wish that we could end class with the law of cosines, because that would really provide kind of a nice unity to the whole course. because we started the course with the Pythagorean theorem, and the Pythagorean theorem we saw all over the place in this pre-calculus course. And the law of cosines is kind of like the ultimate Pythagorean theorem. Okay, it's an extension of the Pythagorean theorem. So it says the following: that if you have any triangle, right? So the Pythagorean theorem only applies to right triangles. Law of cosines is like the Pythagorean theorem, but for any triangle. So it says the following. Again, let's call the angles A, B, and C, capital A, B, and C, and let's call the lengths little a, B, and C. And so the law of cosine says the following, that c squared equals a squared plus b squared minus 2ab cosine c. Okay. For any triangle, you're always going to have this. You always have this relation. C squared, this is not really a hypotenuse, right? All of the side lengths are, equal, right? There is no hypotenuse here. But one side length squared is always the sum of the other two, the squares of the other two side lengths minus this term. Okay. And you see that if C were a 90-degree angle, what am I doing? Sorry. Right? If C were a 90-degree angle, then C would be the hypotenuse. Right? If C were a 90-degree angle, then this little c would be the hypotenuse. And what would the law of cosine say? It would say c squared equals a squared plus b squared minus 2ab cosine of 90. What's the cosine of 90? 0, right? It's the x-coordinate of this point on the circle, right? So it's 0. So the law of cosine says c squared equals a squared plus b squared if this angle is 90. Right, so it encompasses, this thing encompasses the Pythagorean theorem, right? And in fact, it says a little bit more, because it says that the only way that this is going to be true is if the angle is 90, right? So it's kind of giving you a reverse, a converse of the Pythagorean theorem, saying that if c squared equals a squared plus b squared, then this cosine must be 0, which means that the angle is 90. So you can, if you have a triangle and it satisfies c squared equals a squared plus b squared, you know it's a right triangle. Okay, so it's kind of like the opposite of the Pythagorean theorem. Right? Pythagorean theorem says if you've got a right triangle, then this happens, and this tells you if this happens, then it must be a right triangle. Okay, so yeah, remark gives a converse to Pythagorean theorem. Okay, it's just a side comment. Oh, I don't know if we're going to finish up. So we may have a little bit more at the, we'll see. Okay, so again, let's do the applications first, so that you can do your homework, and then we'll finish. We may have to go next time. Okay, so here's an example of the application, and the applications are all kind of not that interesting. They're all the same as before. Right? You're given 3 parts of something and find the 4th. So like here is x for 10, 150 degrees, right? And they say, what is x? Okay, so anybody see how to do it? What are we gonna do? Right? What are we gonna use as our c? We have only one angle here, right? So this is going to be that capital C, right? So Pythagorean theorem says x squared equals a squared plus b squared minus 2ab cosine of 150. Right? Cosine of 150 is negative root 3 over 2. Oops, I should have written A and B here. 2 times 4 times 10 times negative root 3 over 2. Okay. I'm not going to work it out. We just multiply these things, right? So you get x squared is equal to 116 minus 40 root 3's. Plus 40. Plus 40 root 3's. And so x is going to be the square root of it. Yes?
Isn't it 80 root 3's?
No, because they've got a root 3 over 2, and we've got a 2
Oh,
here.
okay, yeah.
So those guys cancel, and we are left with 40 root 3's. Okay. Yeah. Okay, another example. So this was actually 20B from your book. This is 23. Another example. Again, can't read it. 130. 6, 3, 130 degrees, and this is x. Okay. Again, this is not the most exciting thing. Right? We have this one angle here, right? And so we know that the one opposite, right? We know that 6 squared is going to be a squared plus b squared minus 2a times b, 2 times 3 times x, times the cosine of 130. Okay. So we're going to get 36 equals 9 plus x squared minus 6x, 6 times the cosine of 130 times x. So you end up with some quadratic equation, right? So you get x squared minus 6 cosine 130 degrees, x minus 27 is 0. And then use the quadratic formula on it, and there'll be 2 answers, but one of them will be fake. One of them will be negative, and so that won't work. But anyway, it's all kind of the same thing. Okay. I think we do have time to finish up what I wanted to say about the law of cosines. So as usual, the thing is, why should we believe it? So let's suppose that we have A, B, C like this, right? And okay. So why should we believe? Why is c squared equals a squared plus b squared minus 2ab cosine c? Okay, and this is actually the way this works out is actually kind of cool because it actually falls out of the Pythagorean theorem. So it's funny, it's like the Pythagorean theorem implies the super Pythagorean theorem, right? So knowing the Pythagorean theorem actually gives us the law of cosines, which is like a more powerful version of the Pythagorean theorem that includes the Pythagorean theorem, right? So they're actually equivalent to each other. Okay, so we don't have much time, so let me just show you how this works. This length is a, right? I'm gonna call this thing x. Okay, let's call this guy x, and then this guy is going to be a minus x. Okay, and then we're just going to go, as usual, crazy with the Pythagorean theorem. Okay, we've gone crazy with the Pythagorean theorem before, and it's fitting to sort of end in this way. Okay, so what does the Pythagorean theorem say? It says that, let's look over here, it says that x squared plus h squared equals b squared. Right? What does the Pythagorean theorem say on this side? It says that a minus x squared plus h squared is equal to c squared. This squared plus this squared equals this squared. Right? Okay, well that's good, right? So that tells us that h squared equals b squared minus x squared. And also down here we see that h squared is equal to c squared minus a minus x squared. Right? Okay, so let's set those things equal to each other. Let's set those things equal to each other, right? B squared minus x squared equals c squared minus that thing squared. Well, that's a squared minus 2ax plus x squared. Right? So that tells me that c squared minus a squared plus 2ax minus x squared equals b squared minus x squared. Right? I just, subtracted this thing and flipped all the signs. Okay. Now we've got a negative x squared on the left and we've got a negative x squared on the right. So we can get rid of those guys, right? And what we're seeing is that, let's move this a squared to the other, let's add a squared to both sides, and we get a squared plus b squared. A squared plus b squared equals c squared plus 2ax. I'm going to move the 2ax to the other side also. Sorry. So I'm going to move this stuff all to the other side. So we get a squared plus b squared minus 2ax equals c squared. Right? And this angle here is C. Right? This angle here is C. Let's think about, what's the cosine of C? What's cosine of C? What's cosine of C? Melanie, I'm going to make you do it.
A minus x over c.
So you want to think over here with this right triangle here. So
X over b. X over b.
x over b, great, right? X over b, right? So that, what does that tell me? That tells me that x is b cosine c. Right? Let's put that back in over here. Right? We get a squared plus b squared minus 2ax is equal to c squared. The law of two sides. Okay, that's it for today. See you guys next time.